Hey, what's Dr. J talking about today in the signals class? Power and energy signals. What's the difference? As I understand it, I think periodic signals are mostly power signals. And aperiodic signals that do not repeat are energy signals. Aperiodic. What is that? That's just a fancy term that professors make up. Aperiodic means signals don't repeat itself. Looks like you got a handle on this stuff. Not really, it's the math that kills me. Yeah, that math language is something else. Sorry to cut this short. Gotta go. Have fun. And take good notes. I'm taking a couple Z's before going to class. Okay, later.
Hello, Dr. J here. Today we're going to talk about the classification of signals in terms of power and energy. So let's say we have electrical signals, which is either a voltage Vt or a current It. And we know that for Ohm's law, we have a resistor R and that V equals Ri. The instantaneous power in a resistor is given by V squared over R, or I squared R. Because these two equations have the same form, we can let x of t equal v of t as well as I of t, the current and the voltage. So in signal analysis, when we let R equal 1, we just have to deal with one variable, namely x squared of t, which denotes the instantaneous power. Now we're going to take a look at energy signals, total energy as defined for a continuous time signal. And we'll see how the average power is based on this total energy, and that periodic signals is associated with average power. Now the total energy is defined as E equal to the limit as t approaches minus infinity for negative time and positive time for squaring the signal with respect to dt, or more compactly, we replace the t with minus infinity and positive infinity for the upper limit. Now, a periodic signal will not make sense when we integrate because we know that the area will go on forever and ever and goes to infinity. So a periodic signal using this definition of energy does not make sense. Now, the average power is defined as the limit as t approaches infinity, 1 over t, integrating from minus infinity to infinity, x squared dt. Now for a periodic signal, we just need to integrate the average power for one period. So that's what we have here, the lower limit as minus t over 2 and t over 2. A couple more points. We have the periodic signal, and we know that the units of energy is joules, and x squared of t has units of watts, and so when you integrate it with respect to time, then this has joules, and therefore this integral right here is joules. But when we divide it by t, this for one period, then that's equal to the average power. Again, the power signal can't be used here to define energy, and so therefore they're mutually exclusive. So you can't a signal can't be both an energy and a power signal. Now we're going to take the energy and power signals that we talked about, continuous time systems. Now we're going to do it with discrete time signals. So here's our definition of energy, our total energy for a discrete time signal, where we square each value of the discrete time signal and adding them all up from minus infinity to infinity. So that's our definition of our discrete time signal. We also have the concepts of average power and periodic signal. Here we take the power, since we're integrating from minus n to cap n, where n approaches infinity, we're going to do the same thing, square each value, and we're going to divide it by 2n. Now for a periodic signal, it's going to repeat after every n times, so that's why we divide by 1 over n. So here we go from n equals 0 to n minus 1, and square each term of the discrete time signal. So these are our concepts associated with discrete time signals, and we'll do numerical examples associated with these definitions in future videos. Now we're going to take the concepts or definition of power and energy and apply it to a sine wave signal. Alright, so let's say here we have an energy signal. An energy signal basically has zero average power and is usually associated with signals that are deterministic and aperiodic. And aperiodic means that the signal does not repeat itself. So here, notice I highlighted this in red. I'm just going to say that this function is only defined for this time interval highlighted in red. So going from minus infinity, there's no signal. From this point on to minus infinity, there's no signal. And then from the origin to positive infinity, there's no signal. Now, when you square this function, we have an area due to this part of the sine wave and an area due to this part of the sine wave. But adding these two areas will be bounded to be less than infinity and greater than 0. Now, the definition of power is that the limit is as t approaches infinity, where we divide it by 1 over t, and we integrate from minus infinity to infinity, and then square this sine function. This sine function is finite, only defined from this interval to this interval. So this area for this function, the sine function, is finite, but when we divide it by t, which approaches infinity, then the average power for this sine function is 0. On the other hand, when we have a power signal has infinite energy. And for this case, now I'm going to say that the sine function goes on forever from minus infinity to infinity, and you could see that in order for this to be a power signal, it has to be bounded to be less than infinity. However, when we use the energy function definition, we see that this energy blows up, and therefore the sine function, which goes from minus infinity to positive infinity, that can't be an energy signal. So power signals are usually periodic, and we just showed that a sine function will not satisfy the energy definition because it makes this equation blow up. Now for a sine wave signal, we're going to evaluate only for one period. Here I said from minus t over 2 to plus t over 2. But you can integrate over one period, let's say from 0 to t, or from minus t to 0. And you'll still get the same answer. We'll show in future videos that the average power for a sinusoidal signal is basically a squared over 2, where a is the amplitude of the sine wave signal. I'll provide more numerical examples on the difference between energy and power in either here on YouTube or at my website blog at freedomuniversity.tv/blog. Signing off is Dr. J.
Hello, Professor Einstein. Sorry to bother you, but do you know where I can get more information on signal and systems?
You can go to Dr. J's website by clicking on this hot link. Professor Santiago is a YouTube partner, so you can go to freedomuniversity.tv, where he has more tutorial videos in engineering and other topics.
Great, I think I'll do that.